And if you do not heat it and dry it, when you measure the mass, the water being absorbed on the ceramic will be included in your mass. And then you put your sample in there. When you do the heating there, not only the water hydration in the compound gets out, the water absorbed by crucible is also leaving the system there. That will introduce error there. Okay, so if you get a crucible in the lab today and it looks fairly clean to you, then you just go and measure the mass of it. Use the mass of the empty crucible for your calculation. Do not wash it, do not clean it. And the thing here is that you know the mass of the empty crucible, you put certain amount of sample in there. Okay, and then you heat it. When you do the heating there, the heat fetches high from a Bunsen burner there, and you can break the chemical bond between the water molecule and the ionic compound. In this case, water will leave the system and will evaporate in the form of water vapor. You won't really see water vapor there, but you will see for this particular experiment, you will be able to see a color change. Okay? Now, copper sulfate hydrate actually has a very bright blue color. When you start heating it, you're breaking the chemical bond between water molecule and the ionic compound there. Water is leaving the system. You will see a gradual color change from bright blue to pale greenish. Eventually, when all of the water is gone, you end up with a pale white solid. And that's the anhydrous copper solid. Now we know how much we start with, the blue solid. We can also determine how much we end up with. Well, before and after heating, the only thing left the system is water. So from there, you can determine the mass of water that you lost. And we know the total mass of the sample there, so we can determine how many moles of water we lost. And based on the mass of the anhydrous, the leftover after the heating, we can figure out the number of moles of that compound we have. And then this number 5 simply is the molar ratio between water molecule and the carbohydrate. So this is what we do in the laboratory today. So we're talking about determining the formula for different types of compound. Hydrated compound is one of them. Okay, so we can determine the molecular compound, the molecular formula for this particular compound in the laboratory there. And we'll give you some first-hand experience today when you work in the lab there. Okay. Now, another method of determining the formula, empirical or molecular formula for a compound is what we call the combustion analysis. Now, the combustion analysis here is that the idea of combustion analysis is that you have a controlled system so that you know after you have the sample analyzed, that after you have completely burned the sample there, you can collect the product. So this is a diagram using your textbook there, and I'm starting, say, some sample here. You put it in the furnace there, you heat it up. Now, after you also when you do the burning there, you have to supply oxygen. After the burning, and you generate water, you generate carbon dioxide. And assuming this is something that only contains carbon, hydrogen, or another atom, and or another atom there, like nitrogen or oxygen there. Okay, so we can determine the mass of the water being absorbed. We can determine the mass of the carbon dioxide being absorbed. And based on those masses there, based on the mass of the original compound, we can determine the empirical formula of this compound. So let's take a look at how do we do this. Okay, now one of the things that we mentioned there is the steps in determining the formula for new compounds there. One of the things that determine the percent by mass. How do we do this? This is how do we do the percent composite. This is how we determine the percentage by mass from the combustion analysis. Once again, this is another diagram representing the combustion analysis. Now, if you have a hydrocarbon, the term hydrocarbon refers to a particular type of organic compound. It only contains carbon and hydrogen. Okay. Now, if you have an unknown hydrocarbon, we don't know how much carbon in there. We don't know what is the molar ratio between carbon and hydrogen in there. We call it carbon X, hydrogen Y. These two numbers are something that we need to determine. Now, if you burn this hydrocarbon, you get carbon dioxide, you get water there. Now, hydrogen in water comes solely from the hydrocarbon. And carbon in carbon dioxide comes solely from this hydrocarbon. So if you know how much you have here in grams, and you know how many grams of water you collected, how many grams of carbon dioxide you collected, you can determine the molar ratio between carbon and hydrogen. Well, that's all we're trying to do. We need to know the mole ratio between carbon and hydrogen. So based on the mass of water, mass of carbon dioxide, we can determine the molar ratio between carbon and hydrogen. We come up with a formula. Okay. Now this is a situation where you only have carbon and hydrogen in there. What if you also have oxygen in the original compound, like alcohol? Okay. So if you have CH3, CH2OH, ethanol, you burn ethanol in the presence of oxygen there, you still generate water and carbon dioxide. Now, we can determine the amount of hydrogen, we can determine the amount of carbon. But how do we determine the amount of oxygen? Because oxygen now comes from two different sources there. The compound contains oxygen, you are supplying oxygen gas for the burning process, for combustion. So, if we know the total mass of the compound to begin with, and we can determine the mass of hydrogen and carbon, mass is conserved before and after the reaction. So the total mass of the compound must equal to the mass of the carbon plus the mass of hydrogen plus the mass of oxygen. Now the mass of oxygen can be determined by subtracting the mass of carbon and hydrogen from the total mass of the sample. Okay, so here's an example there. For combustion analysis there, say here is a compound that we know it contains only carbon and hydrogen or another elements there. And we burn it in the oxygen gas there. Now, one thing that we have to realize there is all carbon in carbon dioxide comes from the hydrocarbon. All hydrogen in water comes from the hydrocarbon. Okay, and then the oxygen, here's an example of that question. So if you have, say, 1 gram of a hydrocarbon that contains, we know, carbon, hydrogen, and oxygen, and you burn it, you end up with carbon dioxide. You measure the mass of it, 1.5 gram. Water, 0.405 gram. We ask you to determine the empirical formula. So this is an example, and you will see several questions related to this particular topic in your homework assignments there. Okay, so this is an example of how we solve this kind of question, how we solve this kind of problem there. Okay, so we now know we have 1 gram of sample. After the combustion, you end up with 1.5 gram of carbon dioxide. I say, well, you just said mass is conserved. How can you generate more from only 1 gram sample? How can you generate 1.5 gram of carbon dioxide? Well, remember this chemical reaction. You actually added oxygen to this burning process. So carbon dioxide, well, whatever you have to begin with, plus the mass of the oxygen, well, that's where the extra mass comes from. We did not create all those extra masses there. Okay, how do we approach this particular question? Well, we need to figure out, first of all, based on the mass of carbon dioxide, based on the mass of water, how many moles of carbon dioxide, how many moles of water do we have? So we know that each mole of carbon dioxide is 44.010 gram. Each mole of water is 18.02 gram. Okay, so if you have 1.500 gram of carbon dioxide, each mole 44.010 gram. This is nothing new. Dimensional analysis. Conversion factor is the molar mass. Okay, and gram cancels out, and you get the moles of carbon dioxide. You do the same thing for water. There's 0.405 gram of water. Conversion factor 1 mole, 18.0152 gram. Gram and gram.